Okay, so as you can see, this says Graphing Rational Functions Notes Worksheet number 3. And so some of you are actually going to be doing Worksheet 3 before you do Worksheet 2, but such is life of hybrid. So Worksheet 3 here is actually working on doing it the other direction. So what this is going to do is have us take a look at a graph, and then from the graph, can you write the equation? So a lot of times this actually really helps solidify some of the ideas that we talked about last week. So in some ways, I think doing it, taking the time or doing worksheet 3 first actually could help some of you before I see you again in class. So what I would like you to do, when you look, it says that you're supposed to submit both your notes and worksheet 3. So what that means is, watch this video, and as you watch this video, fill in these notes for this first example, and then your homework then is to complete the rest of this. So there's 4 of them for you to try. So that is what you're going to submit on Canvas this week. And in class, we'll continue to work on practicing graphing, and then remember that you have an in-class quiz next week. And if you look there on Canvas, it tells you what day your quiz is, depending on when I will see you, because we don't have school next Tuesday. All right, so for this first one, actually, as you can see, it says group warm-up problem, but since we are no longer in groups, I can't have you do that this year. But if you want, you can pause the video here and try this one on your own if you want. But there are a couple things in this one that are a little bit trickier, and so I kind of wanted to use this as a chance to point a couple of these things out. But yeah, if you want to pause the video and try it, and at least see how much you can figure out on your own, that'd be great. Try that, and then unpause it and see how you did. Okay, so we're going to first here look at the end behavior, right? So if we take a look at this, the degree of the numerator, so the degree of the numerator up there, right, if we multiplied it out, it would be x squared times x squared. So the degree of the numerator would be 4. And then the degree of the denominator, if we multiplied that out down there, we would have an x times an x squared times an x. So that would also be 4, right? So because of that, then we're going to have the same degree in the top and the bottom. So since it's the same degree in the top and the bottom, we actually do need to think about then what the coefficients are. So, if the bottom had been bigger, then we could have just said, oh, it's going to be at 0, right? But this time it is actually equal. So up top then, if we had multiplied that out, right, we would have gotten 2x to the 4th. And again, we don't care about any of the lower stuff, right? So we're going to have an x squared, and we'd have an x squared. And we would have had on the bottom then just an x to the 4th. So that would simplify to just 2. So it looks like we're going to have an end behavior equation at y equals 2. So we'll go ahead and plot that horizontal asymptote. All right, so we'll just go in there, y equals 2. So there's that. Okay. So I like to label my stuff on my graph. I think it's helpful. So y equals 2. Then we have to think about discontinuities, right? So if we look at this, if you look at the bottom, right? So we're looking at the denominator to figure out what those discontinuities are. So we know that x can't be -3, x can't be 1, and x cannot be -4. Right, so we know that those are the 3 numbers that are going to break this function because we'd be dividing by 0. And then again, we have to classify them. So the way that we classify, right, is based on whether things cancel or not. So as you can see, the x plus 3, right, does not cancel out. So since that doesn't cancel out, we know that that's going to be a vertical asymptote. Right, it's an infinite discontinuity. So we're going to have a vertical asymptote at x equals 3. And then if we look at 1, right, so if we look at the x minus 1, that also does not cancel out. So that's going to be another vertical asymptote. So we know we have another vertical asymptote at x equals 1. And then last but not least, at x plus 4 there, you'll notice that x plus 4 does cancel with one of those x plus 4s on the top. And so because that would cancel out of the denominator, we are going to have a hole there. And so our hole would be at negative 4 comma something. Right? And so we figure that out by plugging it back into the simplified equation. Now you'll notice this time, though, that even though it canceled out of the denominator, there actually is still an x plus 4 in the top. And so this happens occasionally. It didn't completely cancel out of the top. And so because of that, right, when I plug negative 4 back into the simplified equation, right, I would have negative 4 minus 2 and all this stuff. But notice I would have gotten a 0 right here. And so 0 times everything is 0. And so I actually then end up with a hole at negative 4, 0 this time. So I don't even need to plug in the rest of it. I can just say, oh, well, as soon as that factor right there becomes 0, everything would be 0. And so this time our hole actually ends up being on the x-axis. So that doesn't always happen, but it did this time because even though it canceled from the denominator, we still had a factor of it in the top. So, all right. And then other things to note then are our vertical asymptotes. So let me graph those real quick. So we had one at 3, and then we also had one at 1. So, I'm sorry, at negative 3. Sorry about that. I just noticed over here I wrote negative 3 on my what x can't be, but then right here when I wrote the vertical asymptote down, I actually wrote positive 3, didn't I? So, all right, so negative 3, but I caught it, so it's not a donut point. So, all right, so we'll fix that. Okay, so at negative 3, we've got a vertical asymptote, and then also at 1, we've got a vertical asymptote. So there those are. All right, so we've got nice looking vertical asymptote at negative 3 and also at 1. Okay, and then we want to deal with our x-intercepts. Right, so our x-intercepts again come from the numerator. Right, so if I set the numerator equal to 0. Right, so I've got 2, x minus 4, and x minus 2 squared. I'm sorry, x plus 4. Gosh, I'm tired tonight. Okay, so there it is. So a couple things to point out, right? When you have a constant out there like 2, right, setting 2 equal to 0 doesn't make any sense. That's not going to generate an intercept, okay? The other thing is x plus 4, we actually already know was where the hole was. So when it comes to x-intercepts, we don't need to list this one because it was the hole. You could list it, but technically it's not an intercept because there was a hole there. So really then, the only thing that's going to be a root or an intercept is at x minus 2. And so that would be then at 2. Right? So we're going to have an intercept at 2, 0. And notice then that it had a multiplicity of 2. So that means that this time it is going to bounce, right? So if I come over here to 2, I know I'm going to have a bounce when I do finally graph this thing. And then the last thing would be the y-intercept. So if I plug in 0 for x, right? So all y-intercepts, we plug in 0 for x and see what we wind up with. So we're going to have 2 times 4 times negative 2 squared, plugging in 0 for x on the top, and then on the bottom we'd have a 3, and then a negative 1 squared, right? So again, that's just plugging in 0 for all these x's, and then having to figure out what it's going to be. So when I do that, up top I would get 2 times 4 times 4, so that would be 32, and on the bottom I'd get 3 times 1, so 3. So it looks like about 10 and 2/3 is where my y-intercept is. So I'll go ahead and plot that. So 10 and 2/3 would be about right there. Okay. Now this may be one of those cases where you're looking at this and say, gosh, that doesn't seem like enough information. I don't think I can graph this thing. And so this is where if you wanted to plot a couple of extra points, you're more than welcome to. But I actually want to walk you through kind of how you could graph this without actually having to plot any more dots. So there's a couple more little things to look at. So I'm actually going to start in the middle here because I know that there's a y-intercept right there. And so if I know that this graph has to somehow fit between these two vertical asymptotes, right? So somehow this curve is going to fit in here. Now, if it fit this way, it would have had to cross the x-axis. So it can't do that, right? So instead, I know that as it comes down, somewhere it must turn and go back up again. And I don't know exactly where, but I know it's somewhere in there it's going to have to turn. So basically, I now know that this thing is going to come in here, and we're just sketching it. So again, we don't know, we don't know where it turns, but we know that it has to turn since it doesn't cross the x-axis between those two asymptotes, okay? So that's the first thing. Now, the next thing is, we know that this is a bouncer, right? We know that because this had a multiplicity of 2, it's going to bounce right here. So if that's true, it's either going to come down and bounce and level off, right? Or it could come up here and bounce, but then see, in order for it to approach this asymptote, it's going to have to cross the x-axis again, which we know it doesn't. So the only way this could work is if it comes down, bounces, and then levels off along there, okay? Now the other thing that's actually interesting to note, and so this is just another kind of new piece of information. I think I might have mentioned it to a couple of the different groups last week, depending on if it came up or not. And that is that at this vertical asymptote right here, so notice that for that vertical asymptote, the x minus 1, see how that factor was squared? So this is like a multiplicity on a vertical asymptote. So I'm actually going to make a note of that right here. So this one actually had a multiplicity of 2 on the asymptote. And so what that actually ends up doing is it says, okay, if the arrow was going up on this side of the asymptote, it's going to be up on this side as well. Okay, so whenever the multiplicity at a vertical asymptote is even, it means that the arrows are going to go the same direction around that asymptote. So that can be another useful, helpful way to kind of figure out what the graph is doing. So now we know it must come down, and then again, we know it bounced at that dot. So then it's going to bounce, and it's going to head off this way. Okay, so it's going to approach that asymptote. And then the last thing is over here, right? We're going to have to put something in over here. So it's either going to be up here, right? But wait, we know it has to cross the x-axis here where that hole was, so it must be down, right? So, and you could have started there even, right? That might have been the first one that you put in because you knew it had to hit that hole right there. So there is that last piece. Another thing to note, just to point out kind of as a check, right? Notice that the x plus 3, right, which created the negative 3 asymptote, was to the first. And so because that was to the first, notice that if it went down on this side, it's going to go up on the other side of that asymptote. So that's another kind of key thing to keep in mind. One other thing to always keep in mind is that, your asymptotes, your vertical asymptotes are essentially dividing the graph up into 1, 2, 3 sections, right? And so you know that there has to be something on this section, some type of graph in this section, and some type of graph in this section, right? So that sometimes people will forget about one of those sections, but just think about those vertical asymptotes, and they're like cutting the page up into those different sections, okay? All right, so that one certainly was a little more complex, had a couple of key things, one being a hole at an x-intercept, another thing being, right, the fact that, when it was squared, it went up, around that vertical asymptote, went the same direction, and then also that we had one of those bounces there, right? And again, as you're continuing to kind of learn how to do this, you can always type that big mess into Desmos, and when you do, I had already done it ahead of time, sure enough, that's pretty much what we got, right? It's looked something like that. Okay, so you can kind of check yourself there. All right. So the main thing is that, as you're practicing this, certainly okay to look at Desmos, but don't forget that next week in class, you won't have access to Desmos. You'll have to graph these without it. So, all right. So if those are all key pieces of information, then let's think about how we could use that information to write the equation. All right, so the idea here is if I have a graph, can I use this graph to figure out what the equation would look like? So a couple things, right, to always keep in mind is that the graph can cross or bounce at the x-intercepts, and that is, of course, based on the multiplicities of the numerator, right? So the numerator is creating the x-intercepts. So anywhere that you have a, multiplicity of 2, right, that's going to make it bounce. Or odd, it's going to cross. And then what we just saw up here in this example is that the vertical asymptotes of the graph can either be on the same side or opposite sides based on the multiplicities of the denominator. Okay, so that's then based on the denominator. So in the denominator, right, if that factor is squared, then that's what caused, like we saw up here, they went the same direction. Okay, if the multiplicity is odd, they're going to go opposite directions around that asymptote. So that's another key thing to look out for. And of course, the degrees in the numerator and denominator affect the graph's end behavior, right? So we know that looking at the end behavior is based on the degrees of the top and the bottom. All right, so all that to take a look here at what we've got going on. So if I take a look at this example, let me just kind of label a few things so we can see here that there is a vertical asymptote at -2. We've got another one over here at +2. Looks like we have a horizontal asymptote at y equals 2. Okay. Looks like we've got an x-intercept there at -1. And then we've got a hole over here at -4. And looks like another hole there at 1. Okay, so lots of key things that we want to try to fit into this equation. So what you basically want to do is put a big horizontal line there to represent our fraction bar. And then we want to come up with the factors that would have created all of these different things and then kind of start working around with them. Now, you'll notice in the homework, I actually had you list things out, right? So what are the vertical asymptotes? What are the holes? Are there any x-intercepts and stuff like that? So to try to help you. But here we'll just kind of talk through it, right? Okay, so looking at this, the first thing I'm going to do is I'll say, well, you know what? I know when vertical asymptotes occur at -2 and 2, so that's going to lead to factors in the denominator, right? So at -2, that would lead to a factor of x plus 2. And then at +2, that would lead to a factor of x minus 2, right? So that takes care of my two vertical asymptotes. But then I actually want to bring in this new idea here about the multiplicities. So if I look at this, I'll notice that at the asymptote here at -2, notice that this thing was going down around that asymptote. So if it's going the same direction around that asymptote, then we actually know that that must have an even multiplicity. So we can go in here and then at that factor, we know that it's going to be squared. Okay, and that is because they're going the same direction. Meanwhile, over here at 2, we can see them going opposite directions around that asymptote. So that means that factor must be to an odd power. So we'll just go ahead and assume the lowest odd power and say that it's to the first. Okay, so that takes care of the vertical asymptotes. Let's take care of the x-intercepts. So if we look here, we've got an x-intercept at -1. So we know that that's going to create a factor of x plus 1 up in the numerator where there would have been an x-intercept. And we'll notice that it's bouncing, right? So since it's bouncing, then we know that that must be squared. Okay. And then the other thing we can see is that there's an x-intercept that actually turned into a hole at 1. So we'll go ahead and put x minus 1 in right there. But because it canceled out to create a hole, we know that x minus 1 must also have been in the denominator. That would have created a hole, right? But in order for it to be a hole at the x-axis, just like we saw up here in this example, right, when the x plus 4 canceled up here, right? There was still an x plus 4 left over in the top, and that is why then the whole ended up at the x-axis. So we know that x minus 1 has to be squared on the top. So that way when the x plus 1, had it canceled out to create the whole, then the x minus 1 would have still been up there to create a whole on the x-axis. And then the last thing we see is another whole over here at -4. So therefore, we know that must be a factor. So at -4, so we're going to put that factor in as an x plus 4 on the top and the bottom. Okay, so that's a whole lot of stuff going on there, but it looks like I think we've taken care of everything, except we still need to make sure that this end behavior asymptote is actually correct. So, based on our equation. So if we look at this, since it's leveling off at a value of 2, we know that for this particular problem, the degree of the numerator has to equal the degree of the denominator, right? That's the only way it'll ever level off at a number, other than 0. So if you saw it leveling off at 0, then you would know you want the bottom degree to be bigger. If you see it leveling off at a number, you know that they have to be equal, right? So if we look here, let's see what we've got. So in our particular situation, this one would have counted, we had x squared and an x squared and then an x to the first. So that would have been an x to the 5th up top, right? And then down here in the bottom, we would have had x squared, and then another x, and another x. So that would have also been x to the 5th. So sure enough, we would have wound up with an x to the 5th over x to the 5th, right? So that worked out well. They are equal degree. But right now, they would actually, because things, if you multiplied this out, you would have just had x to the 5th over x to the 5th. And that would have leveled out at 1. We want this thing to actually level out at -2. All right. So since I wanted to, oh no, that's not 2, is it? I can't count. Look at that. That's actually, I think, at -3, isn't it? All right. Like I said, it's very late and it's been a long weekend. There we go. Y equals -3 is where that asymptote appears to be. So my apologies on that. So we're down there at y equals -3. So that means that we need this thing to level off at -3. So we're just going to put a -3 right out in front. All right. So hopefully that helps for you. And you can kind of make sense out of that, and that my inability to count and recognize that was -3, not -2, didn't throw you off too much. And if you've watched the video to the end, then you should be okay. So hopefully you took notes kind of as you went there, and just try these next few on your own, okay, and see how you do with them. All right, I'll talk to you later.